In this video, I'll go over a topological sort algorithm of a directed acyclic graph. A cyclic graph is a graph that has no cycles in it, basically. Now, what is a topological sort of a directed acyclic graph? It is basically the ordering of vertices of the graph such that for any edge A to B, A appears before B for all the nodes. So here are some examples to clarify this. For example, if you have an edge from A to B in the graph, and there is an edge from A to B in the graph, then in that topological sort, node A should appear before node B. Right? For example, here we have an edge from D to C. That means that node D has to appear before node C in that listing of nodes. D has to appear before A as well because there is an edge from D to A. Here are some ordering topological sorts, and we want to check to see whether they are correct or not. For example, C, starting from C to D, that's incorrect, right? Because we have an edge from D to C, so D has to appear before C. That's incorrect. What about this one? D to A, that's okay. A to F, that's okay. F to E, that's okay. E to C, that's okay. And then comes B. That can't be because there is an edge B to C, and B has to appear before C. Here is another one, one that works actually. D to A to F to E, all okay. So stop at E. There you go. And then start at B and then C. That's fine because B, this is an ordering that you see here. B is appearing after A, correct? B is appearing after A and then followed by C, and C has to appear after E, B, and D. E, B, and D, which is okay. And you can check the last one on your own. Here is the algorithm for topological sort, and it receives the graph. The whole graph is basically passed as a parameter to topological sort algorithm. It has three different lists that are initialized right at the beginning of the algorithm. The result list is empty, and at the end of the algorithm we'll have the topological sort. We have a no incoming list. A no incoming list is a list of nodes that have no edge coming to it. For example, in here, in the picture that we have here, the only node that will go into this no incoming list would be D. There is no edge coming to it. E has an edge coming to it, F has an edge coming to it, A has an edge coming to it. All the nodes have an edge coming to it except D. So D will go into no incoming list. And then you have the remaining edges, and that's basically the rest of the edges. Everything, B, C, D, C, D, A, they're all in this remaining edges, list of all edges in the graph. Now, once that initialization is done, you'll go through this while loop that basically produces the topological sort. The condition for the while loop is that as long as the no incoming list is not empty. For example, in this graph, that no incoming is non-empty. D is in there, right? What you do, you remove the element out of this no incoming list. D is removed, and that would be our current vertex, basically. So the current vertex is V right here. We'll add this current vertex, D, to the result list. There's the result list. So that's how we basically built the final topological sort listing. So it's placed there. And then we define this variable outgoing edges. Remove current V's, that's D in our case, outgoing edges from the remaining edges. So remember, the remaining edges initially has all the edges in there. Now, what are the outgoing edges of D? The outgoing edges of D would be DC and DA. So we are going to remove these two edges, this edge and that edge, outgoing edges from D, out of the remaining edges. And once those edges are removed, what we'll do, we'll look at the outgoing node or two vertex. The two vertex in the code that you see here, the two vertex is the vertex the edge is going to. So two vertices here would be C and A. So we look at vertices the edges go to, and then there's a function here which counts the number of incoming edges to each of these nodes. So we'll count the number of incoming edges to the node. To C there will be 2 incoming edges, and to A there will be none. We don't count the edge that comes from D to A. Is there another incoming edge to A? No. What about C? Are there other incoming edges to C? Yes, there are 2 of them. Now, once these incoming edges are counted, the ones that have the incoming edge of 0 are added, that particular vertex, are added to no incoming list. So in this particular case, for example, node A is added to the no incoming list, and C will not be added to that list. With all that said, so keep this algorithm in mind. We may come back to it. Let's apply this algorithm to this particular graph that we have here. Right. So there is the graph. The result list, remember, we'll have the topological sort basically. No incoming node empty right now, and remaining edges empty right now. So let's go through it. No incoming vertices. No incoming vertices. One is E. There is no incoming vertex, and A as well. No incoming vertex. So we place A and E in there. The remaining edges would consist of all the edges in the graph. So EG is there, AB is there, AC is there, CD is there. All the edges are in there basically. All right, so that's part of the initialization. And remember the while loop in the algorithm, it goes to no incoming list, and as long as there are elements in there, as long as it's not empty, it will remove a node from it. And in this case, let's remove E basically. Right? And then we add that E, remove E from no incoming, add it to the result list. There it is. And then also take away the outgoing edges from E. What are the outgoing edges from E? It is EF and EG. So EF and EG will be removed from the remaining edges. Right? So these are the outgoing edges that you see here. Current vertex is E. And the next thing we do, we look at the two vertex, let's say G. Are there going to be incoming edges to G? Yes, there is one right there. So the in count of G is not 0. What about F? F also has incoming edge to it. So the in count of F is not 0 either. So neither one of them will be added to the no incoming list. Right? So we go back to the top of the loop, and there is another, again, these two edges, EF and EG, are removed from remaining edges, by the way. We go back to the top of the loop and look at no incoming list, and then remove the element in there if it is not empty. So A is removed. That's the current vertex right now. A is removed. And then what we look at this point basically would be the outgoing edges. You have AB and AC. These are the two edges going out of A basically. AB and AC. And then look at the two vertex B. Does B have an incoming edge to it? No, there is none in there. So in count is 0. Same for C. Is there an incoming edge to it? None. So in count for C is 0 as well. right? First of all, I forgot to mention, when we removed A, make sure that it is added to the result list. Here we notice the nodes B and C, both of them, they have incoming edge 0, so both of them will be added to no incoming basically list, B and C, both of them. And AB and AC are removed from the remaining edges. Back to the top of the loop, we'll take C from no incoming. The C, the outgoing edge is CD. The 2 vertex is D. Is there an incoming edge to it? No. In count is 0. So we'll first add C to the result list and add D basically to no incoming list. And you'll go to the next one right there. D was added to no incoming list. C is in the result list. And then once again go back up to the top of the while loop. D is removed. There is D. And what about D? D, the outgoing edge is DF basically that we have, the outgoing edge. And is there another incoming edge to this 2 node? Yes, there is this BF in there. So the in count is different than 0. We are not going to add F to the no incoming list. Now the next step in the algorithm is we look at the no incoming list again. We go back to the top of the loop, look at the no incoming list. B is in there, and we are going to remove B. So I believe that is in the next slide. We are going to remove B from no incoming list and look at the outgoing edge. The outgoing edge is BF, and look at the 2 vertex, in this case F. Are there any incoming edges to F? EF and DF, both of them, they are not in the remaining edges, meaning that they've been visited. So there are no incoming edges to F. So in count of F will basically be 0. Make sure that B is in the result list, and basically we'll add F to no incoming list because the in count of it was 0. Back to the top of the while loop, and then remove the element from no incoming list, which would be F. There it is. F is placed in the result list. And what are the outgoing edges from F? There is one outgoing edge to G. And then we'll look at the count the number of edges coming to G. There are none basically, so we can actually place G in the no incoming list. There it is. That's placed in there. And FG is removed from the remaining edges. There's pretty much nothing is left in remaining edges. We'll remove G from the no incoming list, and basically we'll look at the outgoing edges. There are none. We place it in the result list. There is G, and that's our topological sort of the list. So in this case, this is how we traverse it. This is the topological sort. E, A, C, and D, B, F, and G. And in this topological sort, again, if you have an edge in the graph, the left endpoint of the edge will appear before the right end of the edge in this sorted list.